So in this video, we'll look at the current example first. Now I'm giving you a power series. It has the term x to the power n divided by a factorial term of n. And I would like you to find the radius of convergence and the interval of convergence for this problem. And I assume that you have already watched the previous video as the introduction for the power series. And in this video, we look at a couple of examples as a practice. As a first step to such kind of problem, I suggest that you can apply the ratio test. It essentially means you have to compute the fraction you have, and this fraction is based on the term you have, which is x to the power n divided by n factorial, right? So let's write down the fraction here. For the bottom, we basically have the same term x to the power n divided by n factorial, and for the top, you actually have the same term, but you need to replace n by n plus 1. And as usual, we can actually flip the fraction you have in the bottom. So after the flip, the n factorial term comes at the top. And if you look at such a fraction, I think we can actually cancel out some terms. For example, if you look at the x to the power n, you see all the n powers can be cancelled. And you're left with only one copy of x at the top. And please look at what's happening for this fraction. So basically, you're having a fraction n factorial divided by n plus 1 factorial. And by definition, the top actually has n factors multiplied together from 1 to n. But the bottom actually has one more factor because you are multiplying up to n plus 1, you see. So all the n factors from 1 to n are cancelled because they are common among the top and bottom. So it essentially means after the cancellation, you're left with only one extra factor, which is not cancelled yet. So basically, by the ratio test, it means you have to do the limit n goes to infinity for the fraction. Now the fraction at the top, we have only one term, which is x, and the bottom has n plus 1, right? And please look at this fraction. You can think of x as a constant when n goes to infinity because there's no relation between the x and the n. So basically, it means you are doing the limit calculation for 1 over n plus 1, which is conceptually the same as 1 over infinity, which is 0, right? So basically, it means back to the purple color is the same as 0 times x. 0 comes from the limit calculation, which means the ratio is actually 0. And please note that the fact that no matter which value of x you have, when you multiply it by 0, it must be 0. This fact implies that this 0 is for all value of x. Because no matter which x you choose here, this term must be 0. So by the ratio test criterion, what does it mean? So this fact basically means that our ratio is always less than 1 for all value of x. And by the ratio test criterion, it means it's actually convergent. So I'm talking about the power series. It basically means for all value of x you choose, no matter which one you choose randomly, the power series itself must be convergent. So if you look at the number line, that's the picture we have in this case. The number line basically means you have to shade the whole x-axis by the purple color because now our answer cover all the values of x, all values. And basically, if you try to imagine there's a kind of a circle that cover all the values, so it's kind of like the infinite circle, right? So let me put it down. The answer, the interval of convergence, actually is for all values of x. And in terms of the interval notation, we can use the notation from minus infinity to positive infinity to represent the fact that we want to talk about all the values of x. And how about the radius of convergence in this case? If you imagine that 0 is actually the center, the radius is actually the length between the point 0 all the way up to infinity, right? And infinity is not a number, it is a concept. So you can think of the radius as actually the same as infinity because you want to cover all the values of x here. And that's the end of this example. Let's look at one more. So please look at the current problem now. I'm going to ask you for the same problem. You have to tell me the radius and the interval of convergence separately. And as we said, we can actually use a ratio test. It requires you to do some cancellation of terms based on an plus 1 divided by an. And where we have an to be the whole term here. and it's going to be a big term. For the bottom, we actually have the same term as the one inside the infinite series, and for the top, you have to replace everything we have from n to n plus 1, right? So you're having something like that. And let's do the cancellation of factor carefully. First of all, let's write down the whole fraction from the top. It should be multiplied to a fraction, which is the flip of the fraction in the bottom. So we actually have 4 to the power n at the top, and the bottom is going to be n times x minus 3 to the power n. And please check how many terms you can cancel, top and bottom. First, let's look at the term with the base 4. You see all the n copies can be cancelled, so you're left with only one copy of 4. And let's look at the term with x minus 3. And I think all the n copies are cancelled, you see. So it means you're left with only one copy x minus 3 at the top. And I think the remaining terms we cannot cancel, right? Because n plus 1 and n are not the same factor. So now, what you need to do is to find the limit n goes to infinity for this term. And let's just write it down here. So you have to take limit n goes to infinity for the fraction you have. So please look at the current fraction you have here. You're taking limit of that. And same as before, the term with the x has no relation to the n. So even if you take n goes to infinity, it doesn't affect this term x minus 3. It just stays there. So the thing which is important when we take the limits is actually the fraction n plus 1 divided by 4n. And when n goes to infinity, only the highest power term matters in the rational functions. So it essentially means conceptually you're looking at the fraction n divided by 4n, and n is basically cancelled, so you get 1 over 4 as the fraction of the answer for the limit. So let's come back to the purple color. Basically it means after taking the limit, this part becomes 1 over 4, right? Because that's the answer we get here. So it means now we actually have something like x minus 3 which stays in divided by 4. This divided by 4 comes from the fact that it's a fraction you have to look at. And now, let's apply ratio test criterion for this case. The first important one is that we have to make the ratio less than 1. In that case, by the ratio test, we understand that the power series must be convergent. And let's resolve this inequality. It's the same as absolute value of x minus 3, which is less than 4 now. And you can unravel the absolute value by making it look like this. So it means now the term inside the absolute value must be between minus 4 and 4. And you can add 3 to left and right side to cancel out the effect of this minus 3 by adding 3 like this. So after all this step, basically x must be between minus 1 and 7. And let's come back to our interval notation now. So basically, this inequality implies that for whatever value of x we choose inside the interval minus 1 to 7, we understand that this is the x to get the convergent power series, right? And if you recall the steps that we need to carry out after this step, we have to check the boundary point. But I guess for now, we can write down the radius of convergence first. Please look at it in terms of a circle. So these two are the markings on the left and the right-hand side of the circle. So I guess the midpoint between minus 1 and 7 is actually 3. In that case, the distance between the 3 and 7 and distance between minus 1 and 3 is the same. And actually, this distance both are 4. So it gives you a sense that as a circle, now the center is actually 3. You see, center is actually 3. And I can write down the radius of convergence as follows. So this answer 4 comes from the fact that the distance between the center, which is 3, and the left endpoint or the right endpoint is actually 4. And we at least solve half of the problem, and the remaining is to tell me exactly what is the interval of convergence. And in this case now, the second step is to check the boundary point. You see, there are basically two boundary points. So let's do a checking. So if you replace x by minus 1, and please tell me what's happening to the infinite series we have. So please look at what I've written down here. I'm trying to replace x by minus 1 now to the power series we have. And you see the top here, it becomes minus 4, right? So it gives you a sense that what you have is the power series. The top is n times minus 4 to the power n, and the bottom is 4 to the power n. And please recall that minus 4 to the power n divided by 4 to the power n, we can make it look like this. And it means this term is basically minus 1 to the power n, right? And so let me write it down as a simplified way for this big power series. So basically what you have is minus 1 to the power n times n, right? And can you tell me whether it is convergent or not? The answer is that it's actually divergent. You can actually use an alternating series because of this term, but the easier way is by the nth term divergence test. If you check the limits of this term, you see, I think the limit doesn't exist because this minus 1 term to the power n basically means the sign keeps changing all the time, and now the n itself goes to infinity, right? So it means there's no chance it can be 0. If you recall the nth term test, when the limit is non-zero, we understand that our infinite series is divergent. And let's look at the right endpoint, which is 7. So now you see we just have to replace x by 7, and in that case you're getting a power series. The top now has n times 4 to the power n, and the bottom is also 4 to the power n, and this factor can be cancelled. So basically now I'm asking you to add up all the terms n, which is like what 0 plus 1 plus 2 plus 3 and so forth, because every time you have to add the integer, same as the n here, right? And of course this one goes to infinity, right, if you keep adding like this. So it means at this point once again it's divergent. And I think we have made the final conclusion already. We know the center, which is 3. We know the radius of the circle of convergence, and we also check the two boundary points. Both are divergent. So the final conclusion is like this. We can look at my answer in the black box. The fact is that the power series given is convergent inside this interval, excluding both the endpoints. Because of the fact that we get that for both the endpoints, the infinite series are actually divergent, right? And that's the end of this problem.